minutes. Your phone's join. I think we'll start. Right. Share the screen. Okay. So, guys, so we have been seeing what chapter?
Equilibrium.
Yes, right. So I've been seeing equilibrium. So we just started it. Like I didn't go into the chapter as such, right? So I just told you that equilibrium is where like the concentration of the reactants or the products when it reaches equilibrium is not going to change, right? So I just went into rates, right? So but it's not, they don't ask you questions from that, but if you can understand that particular aspect, you will be able to better appreciate what you're going to study, right? So I told you when I say rate, uh, one second. Right. So when I say rate, right, I told you that it is just change in concentration divided by change in time, isn't it? This is what I told you. And if at all you're going to speak in terms of like you cannot speak about the overall rate of a reaction if you have more than one reactant, more than one product, right? You can speak you can speak rate with respect to either one of the reactant or one of the product, right? So I told you whenever you talk about reactants, you talk about a rate of disappearance of reactants because reactants are getting consumed in the reaction. And when I go for products, you must speak in terms of rate of formation of products, right? So, and I told you that you will be able to find out the rates from the slope. If I give you the graph of concentration versus time, and if you have a graph for like this for reactant, from this, if you can take the slope, you'll be able to find out what is the rate of this rate of disappearance of this reactant R. Say if I have some other reaction like this, I mean, this is for the product P, right? Again, if you take somewhere here, if you take the slope, again, you'll be able to find the rate of formation of products. Okay. So anyways, what I'm trying to tell you is that now I told you from the graph itself, you'll be able to understand where the equilibrium is reached, right? Now I told you whenever the concentration of the reactant and the concentration of product is not changing, right? At that point, you have to mark your equilibrium. So I can mark it here. So at this particular time period, I mean, you see that the concentrations are not changing like at this point, right? The concentrations are not changing. So I'd say this is the point where I reach my equilibrium, right? Okay. So this and all is okay, right? Now, what I can tell you is that, fine. Now, when I look at the chemistry aspects of it, right? When I look at the chemical reactions, right? Chemical reactions, I would say, with respect to rate, right? With respect to rate, how fast or how slow a reaction happens, right? Actually, you will be, yeah. So actually, you'll be able to classify them into two types, right? So the thing which you already know only, so they are called as irreversible chemical reactions and reversible chemical reactions. Okay, now what do you mean by this, right? So, okay, fine. Reversible and irreversible, yes, whatever you think of it, irreversible reactions, you will not be able to convert products back to reactants. But in case of reversible, right, you will be able to convert the reactants back to, products back to reactants. But that's not exactly how it is, right? Now, what I can tell you is that if it's an irreversible reaction, right, irreversible reactions are always spontaneous, right? Irreversible reactions are always going to be spontaneous chemical reactions. That means they are going to be very, very fast reactions, right? All spontaneous reactions are going to be very, very fast, right? Again, you know what you mean by spontaneous. We don't have to do anything for the reaction to happen, right? So for all, okay, now, if it's a irreversible reaction, right, thermodynamically, what is the condition? Hope you understood my question. I'm asking, thermodynamically, if it's a spontaneous reaction, what is the condition thermodynamically?
Del G should be greater than 0.
Less than 0, right?
Less
For a
than
spontaneous reaction, del G should be less than 0. So you have to remember this, people, right? So all irreversible reactions are going to be spontaneous. That means they're going to be very, very fast. Say, for example, one example I can give you is we have sodium, and if you dissolve it in water, right? I know I'm going to get NaOH. Okay, I'll write it down. I'm going to get NaOH, right? Plus hydrogen gas is evolved, right? So this is a very spontaneous reaction. As soon as you make these two in contact, you must have done this experiment in your labs also in your 10th class or something like that. You have the sodium can be cut with knife, a small piece of sodium you take and you dissolve it in water, right? So you will see that the reaction will be happening almost very violently, right? Okay, so those kind of reactions are what are called as spontaneous reactions, right? So the thing is, if you have NaOH and H2, right? Now, will I be able to convert back this to this? The answer is no, right? Because the forward reaction, conversion of sodium plus H2O to water, to NaOH and H2 is spontaneous. So obviously the other side, if you're going to go backside, right? But that is going to be non-spontaneous. That requires a lot of energy you have to give, because spontaneous means you don't have to spend any energy. Non-spontaneous, yes, you have to spend some energy. Okay, right? So the backward thing is not possible, right? At least not at normal conditions, but drastic conditions, yes, possible. That or in other words, the backside reaction is not spontaneous. That's the best way to put it, right? Okay, now that's about irreversible reaction. Now, when I go for reversible reactions, right? Now, exactly what you saw, what is that? When we went for thermodynamics, what we said for reversible process, we said that reversible processes are very, 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 very slow processes, right? So here also the reversible reactions are very slow, right? The reversible reactions are going to be very, very, very slow. So slow reaction, say, now this is a proper, this whatever we represented here is going to be a proper spontaneous irreversible reaction, right? Now, how will you represent a reversible reaction? Say, I can represent it like this. Now, you should use your half arrows. This is how you use. Oh, sorry. Okay, so something like this. A reversibly giving B. This is a half arrow. Or you can even put full arrow this side, full arrow that side. Doesn't matter. Like you just have to put two arrows. That's what it means, right? So A reversibly giving B, right? Now, as I told you, all reversible reactions are going to be very, 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 very slow. That means conversion of this to this, that is A to B, is so slow that at any point of time, B can also start forming A. And that is also going to be slow, obviously. Again, I repeat my statement. So since my reversible reactions are going to be so slow, like A giving B is so slow, that at any point of time, the reaction can reverse itself without you doing anything, right? If I have considerable amount of B formed during the reaction, and I can even have B forming A, the backward reaction happening. But again, that is going to happen in a very slow process, very slow manner, right? Okay. Now what are we going to study in this chapter? Like when in your equilibrium chapter, are we going to deal with both of them? The answer is no, right? Yeah, we are not going to deal with both irreversible and reversible reactions, or in other words, logically, right? Talking about irreversible reactions is not going to make much sense, right? Why? I'll tell you. Say if I want to go something and calculate, right? I want to calculate some numericals, right? Say I wanna have the concentrations calculated after the reaction is over, right? Okay. Now let me add a page. Right. So if I take an irreversible reaction, what will happen? Say I have A given B. Okay. Now say I start with some 1 gram of A and 0 grams of B. Right. Now since this reaction is going to be so spontaneous, when you go for the end of the reaction, say this is at time t is equal to 0. At some point of time t is equal to, right, t is equal to some t. Oh god. Okay. At some point of time, this almost would have become 0, right? And this almost would have become 1 gram. That's how it is going to be. Like, since you have to remember that you have to have the law of conservation of mass should be what is it, valid here. Whatever the mass is there initially, I had 1 gram. Finally, also you should have 1 gram. That's what it means, right? So what I'm trying to tell you is that at the end of the reaction, there will not be any reactant left. Again, if it's a proper ideal irreversible reaction, right? Obviously, if you take the example of sodium and water, almost you will see there will not be any sodium, right? There will be, it's almost 0 sodium after the reaction got over. It will be Na, you will have NaOH, you can have H2, even water can be present because water is a solvent, can act as a solvent, but sodium, which you took in the previous reaction, would have definitely almost gone to 0. Okay. Now if you see here, some things are becoming 0 here, right? Like I have reaction ending up with almost 100% completion, right? So I have a problem with mathematics, isn't it? Say when I want to calculate something, I have a 0 here. Anything by 0 is not defined, and 0 by anything is again 0, right? So dealing with what is it, calculations with irreversible reactions are going to be little tricky, like, or at least we are not going to deal with them, right? So in our syllabus, we are going to deal only with reversible chemical reactions. Okay, because you will be able to appreciate equilibrium, right, more in case of your reversible chemical reactions, right? Now if you want to visualize what will be the equilibrium conditions for a irreversible reaction, it's pretty simple. The reaction gets over, the entire reactant would have gotten converted to products. Again I repeat, right? So if you want to see where equilibrium occurs for a irreversible reaction, right, you will be able to understand that at the end, obviously the equilibrium is where the end of the reaction is reached, and at the end of the reaction you will see that almost all reactant would have got converted to products. Okay, right? But in case of your reversible reactions, you will always see, right, the reactant concentration is never going to become 0 because the process happens so slowly, right? And I told you A can form B, and at a point of time, since it happens so slowly, the reverse reaction can also happen if I have considerable amount of B getting formed there, isn't it? So definitely this concept of getting zeros in any point of, even if you have infinite amount of time, right? So the both the concentration of the reactants as well as the concentration of products are really not going to become 0. So the calculations are significant. That's what significant means, important, right? So we are going to deal only with your reversible reactions. Okay. Now we try to visualize when equilibrium will happen for an irreversible reaction, right? Now we have to understand how will I be able to visualize equilibrium in a reversible reaction. Okay, right? So we'll try to approach that. We'll try to visualize how are we going to attain equilibrium for a reversible reaction. Is that okay? Obviously, in the sense that no forward reaction, no backward reaction should happen. Like that's the condition. Here the condition is Here, in case of an irreversible reaction, the equilibrium condition is the entire reactant should have been converted to products, right? But in reversible, right, no forward reaction, no backward reaction. If that condition you attain, right, so I can say that the equilibrium is reached, right? But again, how are you going to interpret the sense that both forward reaction and the backward reaction is not going to happen? It's not exactly that way. We'll try to look into it. Okay, fine. Say I have a reaction A reversibly giving B. Okay, right? Say I start with 1 mole of A, say at time t is equal to 0, and obviously I didn't have any B, assuming I don't have any B, right? So now the time will go on. Say assume that at some point of time, some X moles, or I'd say okay, some X moles of A would have reacted, and whatever it has reacted here, that will come here, right? Obviously, it depends on stoichiometry. If it's like A giving 2B, right? So if X moles are reacting, I should get 2 X moles. But here it's not like that. You don't have to worry. It's just stoichiometry is 1:1, right? Okay. So in this case, if X moles are 1 mole reacts, 1 mole of B forms. So X mole reacts, X mole of B is getting formed. So out of 1 mole, at some point of time, some X moles are reacting. So that X moles will come here. Say again, I would write that 1 minus X minus Y. Again, some Y moles of A are reacting. Now this side I will have some X plus Y, right? So like this, it will keep on happening. Okay. Now, at a point of time, what is going to happen? Obviously, say reverse reactions can also happen. Say, for example, some X plus Y is there and some A moles of B will react. And what will I have here? I'll have 1 minus X minus Y. Then what?
Plus A.
Here. Plus A, right? Obviously. Right, so A mole is reacting here, minus if I put means it is reacting, it is getting consumed, and obviously that reacted amount will come here. Okay, now say this can also happen, like at a point of time, this can also happen. A can form B, B can form A, but still it has not reached equilibrium, right? Now, when can you understand that equilibrium is happening, right? Obviously, the concentration which I have here, the number of moles I have here and the number of moles I have here, if they are not changing, right, then I'll be able to say that the equilibrium has reached. Now, how will I think about it? It's like this. Say I have this, right? Say now I have one. Now again, say A giving A is giving B. We'll assume that, right? Say 1 minus X minus Y A plus A. Say some B is reacting, some B moles is reacting. Now here what will I have? Here I'll have X plus A minus A plus B. Right now, again, what can happen is whatever the B was formed, again it's reacting minus B. Now, again, what will happen? Here it will be plus B. Oh, sorry. Right here it will be plus B. Again, minus B from this side. Again, it goes to B this side. Again, minus B this side. Again, plus B this side. So, what do you see? You see that, after a point of time, right, the amount of A reacting to give B, right? So some amount of B is formed. Say B amount of B is added, right? Same B amount of B is again going back to A to form this, right? So what is happening here? Even though you see some kind of chemical reaction happening, right? Even though you see some kind of chemical reaction happening, but this particular term, 1 minus X minus Y, X minus Y minus plus A, and X plus Y minus A, whatever I had here, that is actually remaining constant. Is it not? This plus or minus B is going back and coming, going back and coming, going back and coming, right? So what do you see? Eventually, the concentration of A and the concentration of B are actually not changing. Yes, right? Do you accept this fact, right? So whatever, say B is reacting, B is going there, again same amount of B is reacting, coming back to A side, again the cycle goes on repeating, right? So even though you see that actually the chemical reaction is actually happening, right? But overall change in the concentration of A and the concentration of B is actually not changing, right? So okay, again I would say this is the point where I have equilibrium existing. This is how you visualize equilibrium in a reversible chemical reaction. Okay. Excuse me, right? And this kind of equilibrium I call it as dynamic equilibrium, right? Why is it dynamic? Because you see actually something is happening. You see that some amount of A is going there and again coming back and all these things are happening. But overall, the system has actually reached equilibrium. Overall, nothing changes. Right? So hope you understood what exactly is happening here. So this is the point. These two basically is the point where I say the equilibrium has reached, and whatever the concentration, whatever the number of moles I have, right? Those are what are called as equilibrium concentrations of the reactants and products, or say equilibrium number of moles of reactants and products. Okay, right? Any questions? Everybody understood whatever we saw now? I want a S from everybody.
Yes, sir.
Right? Okay. Others? Quick. Everybody understood?
Yes, sir.
Okay. 2.
Yes, sir.
Okay. 3. Again, one more. Okay. 4. Quick.
Yes,
I
sir.
think I have. Yes. 5.
Yes,
6.
sir.
7. 2 more. Okay. Fine. Cool. Anyways, so I think most of you would have understood, right? Okay. Now we'll move on. Now you understood in a reversible reaction, how are we going to visualize equilibrium, right? Okay, now we'll go to the mathematical aspects of this. How are we going to calculate? Is there anything which will tell me whether the equilibrium has reached or not, right? So you don't know, right? Whether there are some mathematical, mathematical, I would say numbers, like some numbers, which are going to help me find out whether the equilibrium has reached or not, right? And one more thing you'll be able to predict is, say if you now in this case, what you took is you had 1 mole of A and 0 moles of B initially. Say what if I had 1 mole of A and 1 mole of B, right? So it's not like reaction won't happen. No, it's not like that. See, please don't think it like that, right? Just because I have equal number of moles both sides, it need not be that the reaction might not happen. Say how can I say it? Now I would say that both are reversible reaction. That is in the sense both the forward reaction and the backward reaction is slow, right? But the B giving A reaction might be little more faster, right? And A giving B might be little bit slower, right? So obviously some reaction would happen. It's not like even though you have equal number of moles, doesn't mean that the reaction will happen. But which side the reaction will happen? If you have some amount of A, some amount of B already present in the mixture, right? Which side, whether the forward reaction or the backward reaction, which will happen? All these things you will be able to predict. Is that okay? Right? Fine. So we will go for that. Right? So for us to understand, for us to appreciate the mathematics part of it, we have to now know one law. Right? So this law, what we are going to study now, you will be studying it again in your 12th class in the chemical kinetics chapter. Like I told you, this chapter and that chapter are heavily connected, right? So that particular law is what is called as law of mass action. Okay, so I wanted to please take down a statement, right? This is an important statement that everybody has to know, and you are taking it down. Take a pen and a paper, and I think you are already sitting with a pen and paper, right? So please take down. The rate of a chemical reaction. The rate of a chemical reaction is directly proportional to the rate of a chemical reaction is directly proportional to the product of active masses of reactants raised to the powers of their stoichiometric coefficients. Raised to the powers of their stoichiometric coefficients. Okay, I'll repeat the statement. Please check whether you are taking it down correctly, right? So law of mass action says the rate of a chemical reaction is directly proportional to the product of active masses of reactants raised to the powers of their stoichiometric coefficients, right? So that is the statement. Okay. Now this statement might look little clumsy if you just read it, because there are certain terms which you don't know there. I think the only term which you don't know there is active mass, isn't it? All the other things are there: product, stoichiometric coefficient, all these things are there. These things you already know, right? So reactants, all these words you already know, but what you don't know is actually this active mass. Okay. Now please understand, active mass is not a big thing, right? So say for example, how will I put it is, I would say active mass is the actual amount of the reactant taking part in the reaction. Again, I repeat, if you want, you can take this down also, right? Active mass, and I can give you the definition for active mass. And I'm going to give you the definition for active mass, right? Okay. It is the amount of reactant or reactant or anything. It is the amount of a reactant actually taking part in the reaction. Actually taking part in the reaction. Okay, fine. So now that you've taken it, like, see, from the statement of active mass itself, you'll be able to understand. Like, see, like, even if I have 100 grams of reactant, right? Say like, not all 100 grams are going to react, isn't it? There'll be something called as activity coefficients, that again is beyond the scope of 11th, right? But not all 100 grams will be eligible for the for it to occur in the reaction, right? So anyways, you don't have to complicate things, right? So generally, active mass can be of two types, depending on what kind of reaction you have. Active mass, yeah.
Can you again say the definition for the active mass?
You want the definition for active mass?
Yes, sir.
It is the amount of reactant. It is the amount of reactant actually taking part in the reaction. Actually taking part in the reaction. Okay, right? But again, guys, you don't have to worry much about this active mass. So actually, whatever they give you, whatever the amount they give you, generally we take all the thing and then we assume that all of them are going to actually react, right? But when you go to higher levels of chemistry, maybe if you do your MSc or BSc or PhD, right? So then you'll be able to better understand what this active mass means. But again, now you don't have to worry about it, right? So active mass means the amount of reactant taking part in the reaction, as simple as that. Okay, fine. Now, this amount which I'm talking about, right? This amount can be of anything. I mean, actually, this amount can be, say, concentration. It can be mass. It can be moles. It can be anything, right? But for our this thing, what is that? What we are going to follow is active mass can be in two forms. One, it can be in terms of concentration, or obviously it is going to be in terms of molarities, right? Or it can be in terms of partial pressures, right? It can be in terms of partial pressures. In the sense, say if you have reactions like, say, something like NaOH plus HCl. So what do you see here? Here you see all these are aqueous solutions, right? So obviously you cannot use partial pressure there. Obviously you have to use concentrations for them, right? But if I have a reaction like N2 plus 3H2 giving 2NH3, now all these are gases. So for this reaction, obviously you'll not be able to use concentration. Then you have to use partial pressure, right? So this, like, depending on the reaction, but only these two, nothing else. Okay, so it can be either concentration or it can be the partial pressures, depending on what kind of reactions you have. Okay, right. Now that is understood. We understood what do you mean by active mass. Now you look at the statement. Now you look at the law of mass action. What it says, right? So if you look at the statement, it says the rate of a chemical reaction, the overall rate of a reaction, right? Now R, if I call it as R, right? The overall rate of a reaction, right? They are telling is, okay, actually, let me make a page for this. And guys, actually, before seeing this, I forgot to tell you one thing. Okay, fine, cool, no issues. I'll tell you now. Okay, fine. So what I forgot to tell you is that now we already visualized how equilibrium is going to happen in case of a reversible reaction that we understood. Correct, right? Now we told that it is going to be a dynamic equilibrium, right? So whatever the amount of A will go there, the same amount of B will form A. Like that way, it is going to be there, right? Now, in other words, if I talk in terms of rate of reaction, right? If I talk in terms of rate of a reaction, right? Now, what you can understand is, say, if I have a reaction like A reversibly giving B, and if I say the reaction has reached equilibrium, at equilibrium, you see that the concentration of A and the concentration of B is not changing, but the reaction is still happening, right? The forward reaction is happening and the backward reaction is also happening, right? But what makes that the concentration of A and the concentration of B to be constant? How can you visualize this? Right? So if I talk in terms of rate, can you think of it? Can you think of the condition in which equilibrium has reached, right? That means the concentration of A and the concentration of B is not changing, but still the forward reaction is happening and the backward reaction is happening. How will you explain all this with respect to rate? Or I would say, for equilibrium to exist, right? Now, what is the necessary condition with respect to rate of the forward reaction and the backward reaction? Can you think of anything?
Sir, could you repeat the question once?
Yeah, exactly. That's what I was thinking, right? So what I'm asking is, I assume that this is a irreversible reaction. A irreversibly giving B is a reaction, reversible reaction, right? So I'm telling that, say I started with something, I ended up with equilibrium, right? So I know at equilibrium what happens. The concentration of A and the concentration of B is not changing. Yes, absolutely true. But is it like the reaction is not happening? No, the reaction is happening. Forward reaction is happening. Backward reaction is also happening, but still the concentration is constant. Both the concentrations are constant, right? Now, how will you explain this? How will you explain this in the sense, what is this? Even though reaction is happening, even though I have reached equilibrium, but still the reactions are happening, right? How will you explain this in terms of rate? Or in other words, what is the condition, right, with respect to rates of these forward and backward reaction so that equilibrium has been reached? Is there anything you can think of? Any condition? It can be a guess. It can be just what you think. It can be your imagination, anything, then bring it on.
Sir, your condition means what exactly, sir?
Say, for example, I told that for a spontaneous reaction, delta G is less than 0. That's a condition, right? So like this, with respect to rate, can you think of any condition for equilibrium?
Mass constant, sir.
Yeah, that's what. This is constant, right? The concentration of A and concentration B is constant. Say, I would say that particular thing which you told can be the condition with respect to the concentration. Yes, accepted. But the same condition, can you think of with respect to rate of the forward reaction and rate of the backward reaction? Okay, Fine. So like, if you can appreciate this, please understand this particular whatever I told you is possible, in the sense reaction is still happening, but still the reaction has reached equilibrium. The concentrations are constant. All these things are possible on and only if the rate at which the forward reaction happens is equal to the rate at which the backward reaction happens. Yes or no? Right? How much ever the rate at which A forms B, the same rate at which B forms A. So that means what? The reaction is happening, but still whatever comes out of A to form B, the same amount comes back to form A again. Right? That means the rate at which the A forms B is the same rate at which the B forms A. And if you find this happening, that means the reaction has reached equilibrium. Everybody except this point, everybody understood why is it like this, right? I can even prove it to you mathematically. So what happened there? I had some 1 minus x minus a or something, right? So basically, if I want to find the change in like rate of a, right, rate RA, if I keep, right, what happened there? So some b, what is concentration of say? Basically, it's going to be change in concentration of a divided by time. Same way, RB will be change in concentration of B divided by time. Right? So what is the change in A when I reach equilibrium? If you can you remember what is the change in A when I reach equilibrium? Change in concentration of A or change in number of moles of A. What was that? Some B, right? If you can remember the letter. So B was B amount of A is reacting, going to B, and some that's again same amount of B is reacting back to give A. Yes, if you can remember, right? So obviously what I can write here is going to be, what is the change in A? Change in A is some B divided by T. And I have to put a minus sign because the delta is negative because the concentration is decreasing for reactants, right? Same way. Now RB will be what? Now RB, same thing is happening, right? So this amount of B, the small b which went there, again it is going to come back to A. So the change in concentration is again B, right? So B divided by the same amount of time. So what do you see at equilibrium? At equilibrium, you are seeing both the rate at which A forms B and the rate at which B forms A is actually same. But till the reaction has reached equilibrium, this might be greater, this might be greater, I don't know. Depending on which is higher, depending on which is faster, that reaction will happen. Say if the forward reaction is faster, forward reaction will happen till equilibrium. If the backward reaction is faster, the backward reaction will happen till equilibrium. But at equilibrium, what will happen? At equilibrium, RF, that is the rate of the forward reaction, will be equal to the rate of the backward reaction. Yes? Understood? This is the point which I missed. Okay, so the condition for equilibrium, if someone asks you, it is you are not anymore going to say that the concentration of reactants and the products are going to be constant. Now the exact definition you're going to give that for equilibrium to reach, the rate of the forward reaction should be equal to the rate of the backward reaction. That is the necessary condition for equilibrium. Okay, right? Fine. So now we'll move back. You will go back to your law of mass action. Is my video on? 1 second. No, video is not on, right? Okay, fine, cool, no issues. So what I was telling is, yeah. So we'll now go. What is the time? 7:42. Okay. So now we'll go back to your law of mass action. Right now we'll try to appreciate the statement. Now study the statement as I read along with you. Right, I'm telling what is it written there is the rate of a chemical reaction is directly proportional to the product of active masses of reactants. Okay, first let me put it like word by word. The rate of a chemical. Now let me put a chemical reaction, random chemical reaction first. Okay, say I have A, small a is the stoichiometric coefficient and big A is the reactant. Okay, B, again small b, stoichiometric coefficient, B is the reactant, gives Cc plus Dd, some random reaction I have. Okay, now if I want to know what is the rate, overall rate of this chemical reaction, what law of mass action says is that this R, like, so okay, obviously you can, this is a reversible reaction also, right? So now you have to specify which reaction you're speaking about, right? So let me speak about the forward reaction, because if you look at the statement, they would have mentioned product of active masses of reactants, right? So depending on which is the forward reaction, the reactants might change. Obviously, for the forward reaction, this is the reactant. For the backward reaction, this is the reactant, right? So you have to be very, very careful whenever you go for reversible reactions. Okay, so that's why I'm specifying it as RF. RF is this, the forward way, normal way, from left to right. Okay, so RF, the rate of this reaction, is directly proportional to what it says, the product of what? Product of active masses. Active masses in this state will take concentration. Okay, product of active masses or concentration of the reactants. So how many reactants are there? 2 reactants are there. So I have to multiply their concentrations, right? Concentration of A into concentration of B. That's what it said. Product of active masses of the reactants. Okay, but that's not there. You have to raise the powers, like product of active masses of reactants raised to the powers of their stoichiometric coefficients. So individually you have to raise the powers. Now stoichiometric coefficient of A is A. So I'll raise the power to small a, and for this I will raise the power to small b. Okay, no issues till now. Any questions, guys?
No doubts, sir.
Okay, right. So that's what the statement said. Very simply, RF, the rate of the reaction, is directly proportional to product of active masses or product of concentration. This can be even partial pressures. You can write PA and PB, no issues, right? So, and one more thing is you have to raise the powers to the stoichiometric coefficient, that is A and small b, small a and small b. Done. Right? So obviously now if I have to make a proper equation out of this, I will remove this proportionality sign and put a constant. So RF will be equal to, say I'll write some constant KF into A power A into B power B. Yes. Okay. So this is a very good thing. This again you'll study in your 12th class. As I told you, this exact equation which I wrote here, you will be studying in 12th also. But we are not going to deal with this for now. Now, okay, let me tell you what and all is this. So this KF, whatever is there, or some K, or any reaction for that matter, the constant you put there is what is called as a rate constant. Right? It's what is called as rate constant. Okay. Now that is about the forward reaction. Done. This is what law of mass action said. Now I included a constant there to get the rate equation. This is my rate equation. Okay. Now if I take the backward reaction, RB, right? Now RB, what happens now? What is the reactant now? C and D are the reactants, right? Now again I can tell that RB will be, will be directly proportional to the product of concentration of the reactants. In this case, the reactants are C and D. So C's concentration multiplied by D's concentration, right? Again, you have to raise the powers also to powers of their stoichiometric coefficient. So C power C and D power D, right? Again, for me to put remove the proportionality sign, I'll put a constant RB. Now the constant will be different. It's not like K, it's not like previous time KF. Now it's going to be some other constant. Let me call it as some KB. KB into C power C into D power D. This place alone, there's a problem. It's not writing properly. Okay, anyways, right? So RB will be equal to KB into C power C into D power D. Cool, right? Now, obviously, now if the reaction has not reached equilibrium, again, this, okay, now I can even call it as KF, I can call it as forward rate constant, and KB, I can call it as backward rate constant, right? Okay, the KF and KB are going to be called as forward and backward rate constants respectively. Okay, now this is what is your forward reaction rate and reverse reaction rate we are speaking about in the previous case. Like when I told you that how do you visualize equilibrium? What is the condition for equilibrium? Right? Now, obviously, until equilibrium is reached, RF and RB will not be same, right? They will be different values, right? But once equilibrium has reached, right? Once equilibrium has reached, as I told you, RF and RB is going to become equal, right? RF and RB are going to become equal. So what will happen? Let me try to squeeze it down here itself. So RF will be equal to RB, and that will indicate that now obviously this and this can be equated now if this is at equilibrium, obviously at equilibrium only, on and only at equilibrium, right? Do not use this for any other condition. Only when the reaction has come to an end, okay, only then the RF will be equal to RB. So that indicates that KF into A power A into B power B will be equal to KB into C. Guys, please bear with this. This side alone, some problem is there. D power D. Okay, so hope you understand. This is C power C and D power D. So these two are equal now. Okay, this you remember, right? Just you take down, we'll go for the next page. Okay, so RF is equal to RB. So I just equated KF in A power A into B power B is equal to KB into C power C into D power D. Yes. Okay.
Sir, D power D or D power minus D, sir?
Oh, wait. 1 second. What did I do? Correct only. C power C into D power D. Correct only.
You put minus D, no, sir, in the second one RB.
Oh, no. This is not a minus sign. This is just a part of the bracket.
Oh, okay, sir.
Okay, I'm really sorry. This is, there's a problem with this side of the screen. At the end of the screen, there's a problem. It's not writing properly. Okay, it's not a minus sign. Proper, whatever you did. Exactly whatever you did here, same thing only you did here. There's no negative sign, nothing. Okay, fine. So done. So this is the equation which I get. KF and KB and all those things are going to be equal, right? Now we'll move on. I'll just make a page. I'll just continue with the derivation, right? So now I'll just rewrite the equation if you want again. KF into A power A into B power B is equal to KB into C power C into D power D. Okay, this is what I have. Right. Now what I do is I will take the ratio of this KF and KB. I will write KF divided by KB. Right. Now what will happen? That will be equal to C power C into D power D divided by A power A by B power. Very simple, right? So this KF by KB is one of the most important chemical term. That is what is going to be called as equilibrium constant, right? And this equilibrium constant is nothing but capital K. See, please remember this rate constants. Whenever you want to use rate constants, KF, KB, whenever you talk about law of mass action, right? All those are small k. That's the notation we use, right? And if at all you want to speak about equilibrium constant, that should be a capital K, Kc, right? Now, what is this Kc? Kc is nothing but the forward rate constant divided by backward rate constant, and that is eventually equal to this, right? C power C, D power D divided by A power A into B power B. And please understand that all these concentrations you're speaking about here are not the initial concentrations, because we are speaking these conditions. We can even make this statement RF is equal to RB only at equilibrium. So they are not initial concentrations. They are the concentrations of all these species at equilibrium, at the end of the reaction, right? Whatever the concentrations are there, that concentration only you have to substitute here. Please be very careful when you're going to do the problem. Initially, they'll give you some amount. Even they can give all amounts of A, B, C, D, but that is not the value you take. You make the reaction happen and you reach equilibrium, and those concentrations you substitute here. And whenever we do problem, that will make more sense. But anyways, you have to remember, that's a very common mistake everybody does. All student does. They will put any random concentrations here. No, you are not going to do that. All these concentrations are going to be concentrations of all these species at equilibrium. Again and again I'm specifying. Okay, and you learned a new thing today. You learned the concept of, you learned the number called equilibrium constant, Kc. Now, what is the C? C is in terms of concentration, since you're using concentration here. Now, I can even have Kp, that is in terms of partial pressure. Say for the same reaction, A plus BB giving Cc plus BD, if I want to write in terms of partial pressures, like the same thing I can do. So this Kp, right, will be equal to PA, partial, sorry, it's not PA. First product should come. You can see, right? This is product by reactant. Okay, right? So PC power C, partial pressure of D power D divided by partial pressure of A power A and partial pressure of B power B. Again, that's my Kp. P denotes pressure and C represents concentration. Okay, so these both are equilibrium constant. This is equilibrium constant in terms of pressure. This is equilibrium constant in terms of concentration. But for both of them, what I'm going to do is that you have to remember the derivation, because they might ask you. Very simple. You write a reaction at equilibrium. You say you go for the law of mass action. You put Rf is equal to Kf into A power A into B power B. Same way you do for the backward reaction. Rb will be equal to Kb into C power C into D power D. Then what happens at equilibrium? At equilibrium, I have the Rf, the rate of forward reaction is equal to the rate of the backward reaction. So if you do that, you will be ending up with this equation. Then what you do? You take the ratio of the forward and backward rate constants, and that ratio is what is called as your equilibrium constant. And that equilibrium constant will be equal to products raised to the power of stoichiometric coefficient divided by the concentration of reactants raised to the powers of the stoichiometric coefficient. Now, or I can even talk in terms of partial pressures PA, PB, PC, and PD. Okay, right? So this is exactly what is called as your equilibrium constant. Okay, now I can even have a derivation relating a relationship between these two, Kp and Kc. Okay, that we'll do tomorrow, right? And one most important point I forgot regarding active mass, right? So please take a note, people. If you have space where you return active mass, you can go there and include this point also. Just include the point as active masses of pure liquids and pure solids is 1. Unity. Okay, the active mass of pure solids and pure liquids is 1. Okay, now why did I say this statement is because, wait, let me give you a reaction, then you might understand. Just let me take 2 more minutes, people, then we'll stop. Okay, this is the last concept, right? So say assume like this, I have calcium solid, or I'll write the reaction. CaCO3 solid, when I heat it, gives me CaO solid plus CO2 gas. Okay, I have this reaction with me. Right. Now, I want to write the Kp for this. Kp means in terms of partial pressures. Okay. Now, what you see, you have only one gas here. The other two are going to be solids, right? So, if you want, you can write, but you generally, not only for the pressures, even for the concentration, Kc equation, right? The moment you see solids or liquids, you don't even have to include them in the Kp or Kc equation. Now, in this case, I can just write the Kp as partial pressure of CO2. That's it. Now, nothing else. I should get the partial pressure of CaO, but it's a solid I'm not putting. It's just 1 divided by partial pressure of CaCO3. Again, I just told you it's going to be 1. Whenever you see in a reaction that you have pure solids or pure liquids, you are not going to include them in the Kc or Kp equation because their active mass value is 1. right? Say if I want to give you another reaction, say in terms of something like, okay, so fine. I can take NaOH itself. NaOH plus HCl gives NaCl plus H2O, and this is a liquid, and all these are aqueous solution. This is also an aqueous solution. This is also an aqueous solution. So if I write Kc for this, how will I write? First the products, right? Concentration of NaCl, and the power, the stoichiometric coefficient is 1, so no issues. Power 1 into, now again what you see here, it's a liquid, so 1 divided by, what do you have? Concentration of NaOH into the concentration of HCl. That's it, right? So what I specified is that whenever you see pure solids or pure liquids in your reaction, please do not include them. You can include them in the sense, just put a 1 in the equation. That's it. So for aqueous solutions and gases only, we do the Kc or Kp equation. The other things are not going to affect my Kc or Kp value. Okay, right? So that's it for today, people. Right? So we learned a lot of things today. Right? We learned about what is your law of mass action, what is equilibrium constant, right? And what is active mass, all these things, a lot of new stuff, right? So anyways, I think this is enough for today. So I think we'll meet on Monday, people. Okay, and we'll continue with this. Any questions till now? Any doubts? Anything you want to ask?
So I have a doubt.
Yeah.
So that's like a confirmation. So solid liquids, we take it as 1, the value.
Yeah.
And for aqueous and gas, we take the coefficient as a power and the reaction.
No, like, yeah, in the sense, you don't even have to include them in the equation. If you have solids and liquids, and if you have aqueous solutions, you go for concentration raised to the power of the stoichiometric coefficient. If it's a gas, you take the partial pressure and you take the power of the stoichiometric coefficient. That's it.
So it has gas as well as aqueous solution.
If you have that kind of reactions, you will use either one of them only, right? Either
so we can take either one.
No. Say the reaction, mostly they will not complicate it like that. Okay. Like even if they give you, say, if I have aqueous solutions as well as I have gases, I generally prefer going for Kc only. That means even for gases, I speak in terms of concentration only. But again, that much complications will not happen, Kanna. You don't have to worry much. Okay. But if I have one equation, either I can use concentration or partial pressure, not both in the same equation. No, that should not happen.
Okay, sir.
Okay, right? Cool. Any other questions, anybody? Okay, I suppose there are no questions. Right? So, okay, thank you guys. We'll meet again on Monday. Thank you so much.
Thank you, sir.
Yeah.